Okay, welcome back everyone. We are going to continue our conversation of stress and strain from last time and how they relate to one another based on the material strength with this idea of tensile testing. So as a short review, if I have a cable or some other structural member and I'm in tension, the way I have shown here, we can talk about these two new concepts that we introduced last time. The first one being stress. And we said the stress is related to this force, but it's divided over that cross-sectional area. So our stress is force over area. The other concept we talked about last time was strain. And strain was basically what the change in length is over the entire length, right? So we had a definition of that said change in length over the initial length. But now, of course, you can imagine that if I have something like this piece of foam and I put a force on it, it's going to change in length without very much force being applied. It's going to have great changes in length, right? We're all familiar with foam. It's very flexible. If I were to take my pen, my stylus, and do the exact same thing, I'm not seeing any change in length with the same amount of force because it's a different material, right? So we need some way to relate our stress and strain together based on the material properties. And that's really what this subject is about with this tensile testing, is to come up with those material properties. Not only for that relationship between stress and strain, which is one of the most important things we'll talk about, but also what happens as we continue to apply more and more force. And what happens to the material? Does it break right away? Does it continue to stretch? And different materials have different material properties on that, right? So with that in mind, we're going to look at this idea of tensile testing, and there's some machines to do this with. We have this in the lab. This was one of our labs. I'm not positive we're going to be able to do it. I mean, it's such a great lab that we may push it later into the semester if we have to. But basically, these machines will operate in the same manner. You're loading up a specimen, a test specimen, and then in this machine, I can see that I would be putting a force on that member, and then over here in the computer, what I'm doing is I'm measuring how much it's changing with relationship to its force, right? And from force, we can get the stress because we divide by the area, and from change in length, we can get strain by dividing by the initial length of that specimen. So that's that's like a $70,000 testing machine. I've actually worked with some students to develop some less expensive methods. It doesn't have to be quite like that. So we can see as long as the same principles are there, where we're measuring change in length and we're also measuring somehow the force. Now in this case, there's a little spring scale up here. It's measuring the force. So we have change in length, force, always the same, right? We could do it with an electronic, with a breadboard to come up with something. In this case, you're turning this handle. It's pulling. There's a wire that goes between those two cylinder-looking clamp things, and it pulls it. So we have the same change in length, which is measured by your electronics, and the force that's measured by that guy there. So there are a number of ways that these machines can operate, but they all work on the same principle, that we have a force and we have a change in length. Now, typically, what we're going to have is a testing sample. So when we look at our testing sample, we'd have something that looks like this, where we have usually some on top and bottom. This will typically be called your grips. And the grip is what's actually being loaded in the machine and clamping on, right? And then it tapers down into this middle section, and there'll be some marks or some kind of indication on where we expect it to change length. We'll call that our gauge length. And that's the reason we have this, sometimes you'll hear it called a dog bone type of shape, where it's wider on the grips, because we don't want that part to actually stretch, right? So if you think about it, the majority of the strain should always be happening where it's a smaller cross section. So the general process is always the same for these testing machines as well. First you load your sample, then you slowly apply a load. And the reason you're slowly applying a load is if you apply the load too quickly, you have these other factors that are introduced into the material properties. It's almost like inertia and the bonding of the chemicals and things like that, or bonding of the particles. So really, the reason we're going slow is because it's almost like treating it as if it's static. Like if we just applied this one force, what would be the strain? What would be the change in length? And so as we are slowly applying this load, what we are going to do is we are going to measure our change in length with this force being applied. And we're going to continue this process up until the material fails. So like I said, I really hope we can do this in the lab so we can see it. I do have a link here. If you want to see that link, you can click on it and watch it. It's basically a testing sample of a metal sample. So we have a link here. We can click on this link. Turn down the volume. So you can see what they're doing is they're clamping the specimen in between these jaws. They are putting a extra little measurement device. This is called an extensiometer. And then as it's being loaded, this is actually measuring the force and the elongation, and is plotting it out on the computer until failure. And at that point, you can download your data and map out what's going on along the process. So if we were to look at a detail of what's going on during that loading process, the way we graph this is we have two axes. On our vertical axis, we're going to have our stress. And we said last time we represent stress with this Greek letter. It's a sigma. And we said stress will be measured in either megapascals in the metric system or in KSI for standard. And on our other axis, what we have is strain. And we said strain we represent with the Greek letter epsilon. And we said strain is really unitless, but typically we'll put them in there anyways, and it would look something like inches per inch or millimeters per millimeter. So if I were to look at an example of what's going on with the stress strain diagram, probably one of the most classic examples is a piece of steel, because steel has some really interesting characteristics that make it ideal for building with, and that's why you see it everywhere, right? Now, with steel, or really with any object, as I apply a load, what I expect is a change in length. So what I would see is the graph has some slope to it, right? Which means that as I go up on my stress, I am increasing my strain. And that happens up to a certain point. And what steel does is steel gets to this place where all of a sudden you're not applying any more load, but it's continuing to stretch. So the curve, in essence, flattens out. So it starts to do something like this. There's a little bit of a taper to it. And during that flat time, what's happening is you're not applying more load, so the same amount of load, but the steel is just stretching, right? And then what happens is it actually goes for round two, and it says, I'm going to be a little bit stronger, and it starts going up again. And it hits this peak part where then it starts to let go and can handle less and less strength until it breaks, until it fractures. So there's distinct areas of this curve that we want to look at. The first being this region where it's linear, meaning it's going up at this constant rate. And this is really where we're going to be in the real world. If you're going to be on that other part of the side, the right-hand side, where it's a flat or it's going up, that's basically failure in an engineering context anyways, because you're building your structure, whatever you're working with, is already deformed to the point when it's the point of no return. But if we are down in this linear region, as load is applied and then released, we're always staying at the exact same shape. So we call this region the elastic region. And like I said, it's linear up until the point, and that point we're going to term sigma y. And I'll label these in just a second. Sigma y actually stands for our yield stress. So it's the stress when the material starts to yield or starts to go flat. And so because of that, this whole section where it's basically a flat part of the curve, we call that the section, the yielding section of our curve. And that happens up until we get to this part where it starts becoming stronger once again. It's great last hope until we get to this maximum point here. And this section is called strain hardening. So basically the material, the way I've heard it described is it has a lot to do with the alignment of the material at an atomic level. And it takes a little bit of strength to get it. It has that last little bit before you reach this maximum amount. And because it's a maximum amount, we call that our sigma U, and the U stands for ultimate. And like I said, then we continue to load, and it starts to decrease down in this last little region. We call this necking. So what necking really is, if you've ever seen this before, is our cylinder starts to get thinner in a certain place, right? And this isn't like the original dog bone shape. I mean, there's still, tapering out out here or whatever. But it starts to get thinner, and what's happening is that's where it's ultimately going to fail, right? Because once it gets thinner, it can handle less force, and we call that process necking because it looks like a neck. And then the one other value that we would be interested in is right at failure. What was that stress at that point? So that's our sigma F for failure or fracture. So summarizing those values, we have a sigma Y, which was our yield stress. And I can define this yield stress as up to the point where it's no longer elastic, right? So the end of the elastic region, or the flat part of the graph. We also have our sigma U, which was our ultimate stress, our highest stress that we can have for that material. And of course, that's critically important because any more than that, and you have failure, meaning the whole thing's going to come apart. So remember, force and stress are related. So when we talk about ultimate stress, we could also say the ultimate force that your object can have before it's going to blow apart. And then the last one we had was our sigma F, which was our fracture or failure stress. And that just means the stress when it failed, what was that value? Now, one really important property in here that we need to look at is happening within this elastic region. So we said within this elastic region where we're going to be operating 90% of the time, or actually it's more like 99.9% of the time, there's a slope to this line. And that slope is a relationship between stress and strain, and it's linear related because it's in that elastic region. So we have a value for this. We call this a capital E, and it's called the Modulus of Elasticity, or Young's modulus. So this Modulus elasticity, or Young's modulus, represented with an E. Because it's slope, we know slope is rise over run. So the rise is how much change there is in stress, and the run would be what our change is in strain. So we can come up with an equation for this modulus elasticity E, and it just says E is equal to sigma over epsilon, or what that says, it is our stress over our strain. Now if we look at the units, well, strain was unitless, so whatever your stress is would be the same unit for your modulus elasticity. So units would be in pounds per square inch, or kips per square inch, or megapascals, right? And we can think about what this slope would look like. Going back to this foam example, if I put just a little bit of force, I have a great amount of strain. That means my slope would be very mellow, versus if I had something more rigid like this guy and I were to pull on it, it wouldn't hardly change at all, so I'd have a very steep slope. So in essence, that slope of the line, or E value, will tell us how stiff the material is. Okay, so now that we have these new properties introduced, I can see that if I were to look at a table like we were looking at before, a table will list these properties for a given material. So what we just looked at was like a steel, maybe like an A36 steel, different colors so you can see a little better, an A36 steel. And now I can see some properties. So we just talked about this E value, modulus elasticity, right? And I can see for steel, it has an E value of 29. Now it says times 10 to the third. So E for steel would be equal to 29 times 10 to the third kips per square inch. So that is massively important because now we know exactly how much our material would deform based on the load. We can figure that out, right? Some other values in here. Well, we talked about the yield strength, sigma Y. Now, with this tension, this is a tensile test, so we're looking at tension. So I can see that steel could go up to 36 KSI before it begins to get to that point where it gets that flat part of the curve. That's the most it can handle and still be in that linear region, right? We also have the ultimate strength. We just talked about that. That's the largest value you can have before failure, and steel is 58. Now that we have this understanding of stress and strain in the relationship, we could look up any material we want And we could say, well, we're using 2014 T6 aluminum. We're going to give this much force to it. How much is it going to change in length? How much can we expect it to change in length using this modulus of elasticity? As long as we're in that linear elastic region where we typically are. Now, a lot of materials, you'll notice the ultimate strength and the yield strength are basically the same value. Or actually, what they do in this one, it looks like, is they don't have a value at all. So the reason they don't have a value is because the material, in essence, doesn't yield. So cast iron, you may have heard this term before, it's brittle. And what brittle means is that if I were to look at the stress-strain diagram, it would have that linear elastic region, and then it would just break. So it just goes up and then snap. It doesn't have that stretchiness to it, right? That elastic, that ductility. So let me define those terms real quick. So if we're talking about something that's ductile, like steel, what it means is that we have large amount of strain, a lot of stretching before we hit failure. So like our example before, steel is a very ductile material. That's what makes it gives it a ton of advantage, because if I overload, then things aren't going to break. Instead, I would have this large area that has a flat part of the curve, right? The opposite of that would be brittle, like we saw with that cast iron. And some examples of that would be concrete or cast iron, like we just saw, where you end up with a stress strain. I should be labeling these things. I should be better about that. That just goes up, and that's it. And then failure is right there. So another topic we can talk about outside of the ductility and brittle is how much energy is stored within this material, or how much energy does it take to either fail or to bring the material into the yielding range. And energy is actually fairly easy to calculate. It is just the area under that stress strain curve. I think I have a picture in here. There it is. So here you see we have these two materials we just talked about. For brittle material, it goes up and it just breaks right away. If we want to look at the area underneath that curve, there's not a whole bunch of area. Versus if I had a ductile material like our steel, it can go up and over, and we end up with all of that area underneath this curve, right? So, and basically that's the amount of energy that can be absorbed by the material before failure. And so if you were, say, designing for an earthquake, I think I mentioned this last time, the steel buildings would still be standing after an earthquake, where concrete buildings tend to fail. And that's because it takes all this energy, or the steel can absorb all this energy. It's that whole bending but not breaking thing, is it's moving back and forth and waving with the earthquake, versus concrete is very brittle, so it doesn't have that ability to absorb the energy, and it fails right away. Now, with that same idea of energy, there are two terms that we should be familiar with, and those are resilience and toughness of the material. So for resilience, what resilience is when we talk about material strength is the ability to absorb this energy and go back to its original shape. And like we were saying before, if we were to look at our stress-strain diagram, if we were in this elastic, linear elastic region, you can imagine we load our sample. Now, if I get to this point and I were to remove my load, it would go back that same line. So it didn't change shape at all, right? I end up back at my original shape, and my strain all goes away. This is true up until I get all the way up to this point where I get up to my yield point. As long as I'm below that yield point, when I release the load, it always goes back to its original shape. So this is our idea of resilience. By the way, if I were to keep going, and say I were to go to here, along that yielding section, and then remove the load, it still would decrease its length, but what happens is it's actually parallel to that original line. So I never get back to that original shape if I have, and it's like bending a paper clip, and once you bend it, it's permanently bent, and when you bring it back, I just never end up with the same shape that I started with, and the further I am in that yielding section, the more deformed it actually is. So with that in mind, when we talk about resilience, in defining it, like I said, it's the ability to absorb energy and bounce back. And as I showed on the graph, what this means is this is the area under that elastic region. So if we were to look at a stress strain diagram, say of steel, where steel went up and then it went like this, then it went like that, whatever it might look like, we're really only talking about this area here, which would be easy to calculate because it's a triangle, 1/2 the base times the height, so you could find that area. Now, we also have this concept of toughness. So what toughness is the ability to absorb the total amount of energy before failure. So this is more like we were talking about with the earthquake bit, right? How much energy can steel absorb before fracturing. So this would be the area under the entire curve. If I were to draw that out and look at our stress strain diagram, say, of concrete. We haven't talked about concrete much. Concrete actually looks more like this. It's pretty cool. It's just it doesn't have as nice of a linear section. The whole thing is moving around. But when we're talking about the area for this toughness of, say, concrete, it'd be that entire area underneath the curve. All right, so let's take a look at a quick example. All right, so in this example, what we have is a stress strain diagram for this rod. We're assuming the rod is 200 millimeters long, diameter of 20 millimeters, and we want to find the elongation of the rod when loaded by 149 kilonewtons and the energy stored by the rod at that point. So some key points here are you have to keep straight the difference between stress and force. So if I look at the terms, if I see some key words here, what I have here is it's loaded by 149 kilonewtons. Well, kilonewtons isn't a stress, that's a force. But we said last time we can convert that. So what I would do is I would start by saying, let's find the stress. We said stress is equal to force divided by area. Well, my force here is 149 kilonewtons. Now, I want everything in newtons and millimeters, so I would say this is 149,000 newtons because there's 1,000 newtons in 1 kilonewton. And then the area. I'm not given the area. Instead, I'm given the diameter. So the area is, well, you know, area is pi r squared. You can also use the equation. I think we talked about this before. Pi over 4 times the diameter squared. So now we do have a force over area. We end up with a stress, and our stress, if I did that math right, I got like 474.28. And the units, if I'm in newtons and millimeters, then my units would be megapascals. So now I can just plot this onto the graph and say, what is the 474.28? And that's about 475. I tried to make it somewhat easy. So this would be halfway between 450 and 500, right? That's like 474.28-ish. Well, if that's 474.28-ish, and I carry it over, and then I can come down here, and I mean, technically, I suppose you could just, you know, eyeball it and say, where is it on that range? But like I said, this whole thing is linear. This section is drawn as linear. If this is halfway, 474.28 is halfway between 450 and 500, then I know the strain would be halfway between 0.00225 and 0.03. So that halfway mark is 0.00225 plus 0.03. Divide that by 2, and that halfway mark then would be like 0.016. Units would be millimeters per millimeter. So that's our strain. Now, we can get the strain from the graph, but that wasn't the question. What did the question say? The question said, what is the elongation of the rod? Well, that means how much did it change in length? Well, this is 0.016 millimeters per millimeter of the original length, right? Because we said that strain is equal to our change in length over the initial length. So in this case, we have strain, 0.016, and change in length is what we're looking for. I'm just going to put that delta L, make it a little easier. And then what's our initial length? Well, that was given as 200 millimeters. So that means our change in length would be equal to 200 millimeters times 0.016, which is what? 3.2 millimeters. Now there is a part B. It says, what is the approximate energy stored by the rod? Well, that's kind of a pain because that means I'd have two areas to look at, right? So we said energy is area. Well, I have one, which is this triangle here. Actually, I have three areas, don't I? Because I would probably do it something like this. Oh, this is a rough problem. I would never give anything like this. This is awful, awful problem. But I end up with three different areas. I have a rectangle and those two triangles. I don't know. Like I said, I probably wouldn't do something like this. But if you wanted to do that extra little bit, like if we were to say what's the area, what's the resilience of this material, that'd be much better, right? Because that's just the area of that one little triangle. But anyway, so what's the total energy at that point that's stored by the rod? I have 1/2 the base times the height is the area of a rectangle. So this is this 0.0025 is my base. So this is this area right here. I could call it area 1, right? And that would be the resilience of this material. 1/2 the base times, and then how high is it there? It's 450. And I'm going to add on this rectangle. I'll call this 2. And that rectangle I know is 450 for the height. And then that base, well, what is this length right here? Well, I know that it's 0.016 from here all the way over to there, but I have to subtract out that other little bit. So I'm going to subtract out 0.00225. And last but not least, the third triangle, 1/2, its base is that same 0.016 minus 0.00225. And then the height of that one would be the 450 minus, sorry, the 474.25 minus 450, which is 24.28. So adding all that together, I ended up with an area of 6.86 megapascals. But really the important concept to get here is that energy is equal to area, and I can figure out stress and strain relationships based on the slope of that line in Hooke's law, or I can just interpret it straight from the graph is what I did in this case. So I know that was a lot of information. Hopefully it was somewhat useful, and maybe we can play with this in the lab soon. I look forward to talking to you all later. Thanks. Bye.